let me review what this question is about, and I'll show you the picture, and then I'll give you a minute to take your guess as to what is going on. So the point is we are moving to a situation where this is not what I want. This is what I want. Okay, we're moving to a situation where we have data, and the data we have is the angle that you shot the cannonball at, and you want to use the data. You have to predict something. So in this case, we're using the x value to predict the y value. We're using the angle that the cannon was at when we pressed the shoot the cannon button to predict how far it went. And the thing we established last class is even though we have these 30 data points that are in black, that are x, y pairs, the thing we actually want to get is the true value, which is this blue curve. And in real life, of course, you will never get the true value, but we sort of imagine that there is a platonic ideal out there. There is a blue curve out there that we are trying to get as close as we can to. And we even mathematically defined it. So that is the definition of the function f. And f is this thing. This was all from last class. F is this thing. It is the expected value of y given the x value. And why is it the expected value? That is what we talked about last class. The expected value minimizes the square loss. So that's why it's the expected value, not the median or not the mode or something. We want to minimize the square loss, and that's why we have this. And so we've just added this new thing, which is the conditional amount. And then we measure our loss function, so we come up with some kind of f hat. And by the kind of logic we had before of splitting it up into the error due to variance and how far off we are, we had this decomposition, which says that the loss function for some f hat is how far away are we from the true value squared plus the variance. And this is very analogous to what we did before. Before we had any x data, we had a very similar formula. Let me see if I can find the similar formula. The formula we had before looked like this. So it was our estimate y hat minus the true expected value squared plus the variance. And now it is our estimate f hat minus the true f squared. And the only difference, so it's f hat minus f all squared. The only difference is now we have to average over all the possible x values. And that'll tell us how good or bad we are doing with our estimate f hat. And we want to come up with a good estimate f hat that sort of minimizes this thing. Of course, we'll never be able to get rid of the variance. That will always be there. That's the sort of irreducible error. If we had f hat is exactly equal to f, then this part would be 0. And then we'd be so happy we would have the minimum possible error, and we would jump up and down and shout hooray. Okay, that's the setup from last class and the cannonball problem. This cannonball problem is going to, all of today is going to be deep dive on this cannonball problem. So if something is not clear about it, it's good to clear it up sooner rather than later. Are there any questions or comments about the cannonball problem or what the goal is here, what we're trying to do? Okay, so let's do the first mathematized question then. And the first mathematized question is about this idea of do we want the window size to be large or small? So if you remember, the window size is how we're going to estimate things. So we're going to come up with our function f hat by using a little window. So and in particular, if we want to estimate the value f hat of 45, how do we do f hat of 45? We put our slider here at 45. We do a window centered at 45 of some width. Over here, I guess I have done a width of how big is my width? My width is 7.5. 7.5 degrees. So any cannonball shot between 45 plus 7.5 degrees and 45 minus 7.5 degrees, any cannonball shot with an x value somewhere in this window, I average them all together. In this particular case, there were only 2 cannonballs with those values, and so I averaged these 2 things together. And the very last thing we left off on at the very end of the previous class is we said, do we want a really small window, like a really teeny tiny window, or do we want a really big window? Which is better? And the thing that makes this hard is that in some ways having a bigger window is better, and in some ways having a smaller window is better. So there's no clear answer on which is which. And so that's the first mathematized question, is what is good about making the window size larger? And this one I let you write some words. You should try to keep it to like 1 word. If you want to do 1 or 2 words, that's okay, but don't do like a paragraph. Like 1 or 2 words, okay. Maybe 3 words. I'll make 3 the maximum, okay. And then this one I think is a choice. So if you make it bigger, that's bad because we will blank the true value at x equals 45, and I have underestimate and overestimate and maybe something else. But that's the warm-up sort of question to get us in the headspace of thinking about the cannonball problem. Questions or comments? All right, let me set you free for a minute to finish off this mathematized question, and this will help us discuss how we find the best possible size delta. Okay, a couple of seconds left here. Put in your guesses. I think some people are still going in. Put in your best guess. We're going to discuss the answers. Okay, 19. Okay, that's approximately the number of people in the room. Okay, let's see what you said. So making delta is good because, and there is one main idea, but there's lots of different ways to express it. We won't overestimate. I actually going to talk about overestimate and underestimate in the second one. Some people wrote low variance, and I think that is technically true. Like it is technically true that it has low variance, but I think there's a more fundamental way to describe it. So it's like this is correct, but is not as helpful for if you wanted to explain to somebody on the street. You're like, it's good because it's low variance. We're like, what does that mean? I would say it's good because of some other reason, and this other reason is also why it's low variance. So it's correct, but not as helpful. Okay, this one I love. It would contain more points. This is essentially the simplest possible thing. When you make delta bigger, you conclude more points. So let's go to this thing. Look, the bigger I make it, the more points I include. And we just, at the beginning of class last time, we said more points is better. We did this whole calculation of calculating what's going on, and we concluded that the error in the epistemic error goes down like 1 over the number of points. So if you have 20 points, that's 1 over 20. That's a lot less than if you have 5 points, that's 1 over 5. So it is this idea of just having more points is everything else being equal, that is better. And in fact, I think I wrote that down. Did we write that down somewhere? All else being equal, more data is always good, all else being equal. So is it ever worse to have more data? No, it's always good to have more data as long as everything else is equal. We're going to see that in this case, all else is not equal, and so there is a trade-off. But this idea is the pro of having a big window is you get more points. And I'm sure other people put this in other ways. More data. I don't know about margin. No, in fact, I would say this margin one is confusing. There's something called a maximum margin, and this has nothing to do with that. So margin is probably not the way to think about it. More points, very nice. Larger n reduces variance. This is the connection between the points and the variance. The thing you can think of is that the number of points is exactly controlling the variance of our final estimate. And that was what we saw last class. So we said, look, we have this last class, we had this thing. We had the empirical average of all the points. And then we said, how far away is the empirical average minus the theoretical average? And we did a whole bunch of calculation to show that this difference was size 1 over n. So when you average n points, the empirical average is within 1 over n of the theoretical average on average. So this is why this is better to have more points, is the variance of this quantity is like 1 over n, and so you want to make n as big as you can. So this is a great connection, and yeah, so I think the simplest possible thing, more points, and then more points means lower variance, and therefore lower variance is also a correct answer. So very, very nice. And again, this is the reason more points are better is because fluctuations, like random fluctuations for every individual point, count for less. So maybe you have some random ups, some random downs. If you're averaging 100 points, each of those random ups or downs is only 1/100th of your data set, and so things are less wild. Very nice. Okay, So very, very nicely done over here. Any questions about this? We're going to analyze this sort of in a second, maybe in more detail. I keep losing track of the window. But that's the main idea. Bigger window, more points. More points means the empirical average, the average of all the points, is closer to the true average, and therefore we have less variance, and those are all good things. Questions or comments about that one? All right, that was the pro. Now let's do the con, the other side of the business. It's bad because we will blank, and about half the people wrote underestimate, and about half the people wrote either overestimate or something else. So this one is important to get clear. So something is going to happen that did not happen before. This is the new part. This whole line is the new part that did not exist before we had x values. So if you look at what we did before over here with the 1 over n y1 plus plus yn, the more points you do, the better it is. This is always on average equal to this, but now it is no longer on average equal to that. So if you look at our new thing, we have f hat of x minus f of x, and even if you make f hat of x, if you have many, many, many points, if it's not right on average, we're going to have some problems over here. And in fact, we can further decompose this thing into the so-called bias variance decomposition, and we can split this thing up. Let me not use the giant marker. Let me use the merely large marker. We can split this up into two pieces. Split into two parts. Two parts. And the two parts are called the bias and the variance. Of course, there already is a variance. So this is there's going to be two variances. There's the bias and the variance of the f hat, and then there's the irreducible error, the variance of the y's. So let's do that. And so the split is this is the so-called bias variance decomposition. Okay, and we're going to split this thing into two. Let me write the whole thing down so that we don't lose track. And again, this is on average what happens to the loss. This is the question. So f hat, and we're doing the average over the training samples, the training. So before, the formula was for the average over this averages over the test data, the y and the x. So f hat, we already computed the f hat, and now we're going to average over the training. This is exactly what we did last class as well. So if this averaging on averaging is confusing you, I would think back to this analogy, right? We had, for a given y1 to yn, this was the loss with the empirical average and the theoretical average. And then to analyze how does this do, on average, we took the average over the training set. So we took the average over the y1 to yn, and then we did a bunch of calculations to figure out what it is. That's exactly what we're doing now. And when you do this, what you end up with, so you're going to have some average over all the x's, x1 to xn, y1 to yn, of, and then you're going to have the average over the x of, what do you have, f hat of x. And I'm going to write it like this. Let me leave some space, minus f of x, minus the true f of x, plus the variance of y given x. And now I'm going to do the same trick as before, is I'm going to add and subtract something so that I can use the Pythagorean theorem for random variables. And the thing I'm going to add and subtract is exactly the average of the f hat. So the average of the f hat minus the average of the f hat. So I'm taking what I did before, and I'm just adding on the average of the f hat and subtracting it, just like we did before. And this average is exactly over the x1 to xn and the y1 to yn, the training average. The same kind of thing that we're doing over here. And then the whole thing will split into two pieces by the same Pythagoras trick as before. So now we get a split into two parts. There's going to be one part, which is how far is f hat from its mean? So we're going to get the expected value of x1 to xn, y1 to yn of, and let me write this one, I guess, in green, f hat of x minus the expected value of f hat of x. Okay, and then this is all squared. This is what people call the variance, right? So f hat is sometimes larger than its mean, f hat is sometimes smaller than its mean, If it's jumping up and down all over the place, then how far away is it when you square it will be a large number. That's what we will call the variance. And I think you should think of this as how much it jumps. How much does f hat jump around? Jump around. But then the other part of the equation is the difference, this expected value of f hat minus that thing. Minus that thing. And in that situation, you get this formula. And because there's no f hats anymore, there's no x1 to xn anymore, it is just an expected value over x. So this is a different expected value. Let's do it in brown. Expected value, just the test point x. And then we're doing minus the expected value of f hat of x minus the true value. The true value. And I'll do this in brown. Okay, minus f hat of x. And that is all squared. Yeah, okay, sure. Okay. And this thing people call the bias. The bias. Why is it called the bias? Well, this is saying, look, when you run your problem, your f hat, based on the thing you have chosen, the procedure you have chosen, the f hat you come up with may not be near the real thing. There is a mistake on the board. That is a very important mistake. Let me fix it. There we go. Now it is correct. So this is how far is my f hat on average from the true value f. And the fact that this is the true value is very important. Let me emphasize that. This is the true answer that we're looking for. And this is the average of our procedure. The average answer our procedure gives. Yeah. The average value that our estimate gives. Yeah. Gives. Okay. So this is called the bias, and this is like how far is our procedure on average. Okay. And this did not exist before when we didn't have any x values. This was just 0. There was no, our procedure was on average exactly correct, but now it is no longer exactly correct. Let me show you what I mean by that. So the y's, if you average the y's, what is the average of this average? It's exactly that average. The average of the empirical average is the theoretical average. So there is no difference between the two. And if you have a procedure that is so-called unbiased, you can arrange it so that you're on average correct. But if you pick a different procedure, you may have this bias term may be significant. And indeed, in the one we picked, the bias term is significant. Let me show you a picture on how you could visualize this. And what you want to do is look at this purple dot, and to visualize what it is doing, I'm going to press a button that gives us a new data set. And when I get a new data set, we're going to have a new sample for this estimate. And if it's jumping up and down sort of equally above and below the blue line, that means it is unbiased. It is equally likely to be above or below. That would be great. But if it's consistently jumping on one side, if it's consistently underneath or consistently above, that would be biased. That means we're not getting the right answer on average. So to do this, all I have to do is go down to where these things were created, and I go to where it says generate data, and there's this seed. And if I change the seed, I get a new data set. So if I change it from 1, that's where it was before, now it's 2, new data set. And then I get another data set, and then I can get another data set. And if I hit animate, it should just give us new data sets all day. So this is once a second, we're getting a new data set. And we apply our procedure, and we get this purple estimate. And we're trying to estimate the value of the blue curve here. So we're trying to get this value of 10, and we're getting these values. So here it's here it's there, here it's down there, here it's here. And the question is, first of all, could we be unbiased? That would mean we're on average correct. Or we could have an overestimate, or we could have an underestimate. And that is what the mathematize is asking you. So now that we have defined these terms a little bit more correctly, and I have a little animation, I'm going to open it up again. Do you think we're an overestimate or an underestimate? Before I open it up one more time on mathematize, any questions about anything that I said? Okay, let me open it up one more time. Do you think it's an overestimate or an underestimate based on what you're seeing here? And then we'll puzzle through how you could logic it out directly without that. Okay, so I guess I want to press this button, and then I want to hit duplicate. Okay, here it's open again. Is our estimate, is it an overestimate or an underestimate based on the picture? And okay, I guess this one you can put any word you want that we talked about already. Sure. No, that's fine. Yeah. Okay, just a few seconds left. I think one or two people still have to answer. But let's see what you guys said in the second vote. Okay, this time 16 people said underestimate, only 6 people said overestimate. The correct answer is indeed underestimate. And the key is we are an underestimate of the true value. So let's go back to Desmos. The way you can see that is we are below the blue curve. So this purple dot is sort of consistently below the blue curve. And if we were to calculate where the purple dot is on average, right, it's hard to see where it is on average. All we can see is samples of it, right? So we get a new data set, we run this complicated procedure of averaging, but it looks like it's pretty consistently below. Another way you could sort of see is I could plot this as a function of the position, which is the function estimate. So this purple curve is what would happen if you did this estimate at every single point. And you can kind of see it's pretty consistently an underestimate over here, and then in the corners it's kind of an overestimate. So our procedure of doing this average of all the things that are within a big window is underestimating in the middle, and it's overestimating near the edges. That is a fact, and this is a source of error. So when we go to calculate the error, the fact that we're sort of consistently underneath is one source of error. And that's what the bias variance decomposition tells us, is that if we take how far away this is on average, if it's always like two units on average, we're going to get an error term that is 2 squared in our error, so 4 units. That's what the bias variance decomposition tells us. The other term, by the way, in the error, the variance, that tells us that if it's jumping around a lot, that's also going to contribute an error. And you'll notice actually in this little thing, it's consistently sort of around here. Like it doesn't leave this zone very much. So we're kind of consistently underneath, but we're not jumping around a lot. We're not jumping around a lot. And if I did the opposite way, I made the window very small. So I make the window really, really small. Then what's going to happen is I'm sometimes above, sometimes below. Now I don't have any bias. So like this thing, even though it's sometimes way above, it's also sometimes way below. And sort of on average, this gets it correct. So the purple dot is on average very close to the blue dot. But because it's jumping around so much, I have a big source of error in the variance. And you can sort of see this function is like a really wild function that's going up and down and up and down. That has a lot of variance, even though on average, the purple curve here will be that blue curve, or very close to it. So those are the 2 sources of error, and you have to balance them to get the best possible thing. And in this situation, that means finding the best kind of window size that is not too big, not too small, but is like Goldilocks just right. And I think you can sort of eyeball it. So like this, to me, this is like obviously too small. You can see one hallmark of having this like too small window is that we're chasing down points that are off the blue curve. So maybe I can pause this for a sec so I can talk about a particular one. Let me pause it here. So look at this. There was one point up here that was way higher than all the other points. And our purple curve chased down that point. It's like, oh, the function should go way up there. That does not seem wise. We should probably make the window a bit smaller so that it is a little bit nicer. So something like that seems way better already over here. So even though this point is way up here, it doesn't affect the purple estimate too much because the other points are close enough that to pull that one down, right? So that seems much more reasonable. If I keep going though, you'll see that the function sort of gets too flat, and that's not good either. So this is probably too far. So the window size that I want will balance something like that. Not too crazy, not chasing down the points too much, but also not spreading it out too far either. That is the art that we're going to try to figure out how to do in a second. So this does go by bias variance decomposition, and it is true that this one with the window size too small is high variance and low bias, and the other version, this is low variance, it's barely changing, but it is high bias because it's really underneath, it's very far underneath on average. But it is also equally good to say underfitting and overfitting. So overfitting is this situation where you are chasing down the points too much. You're being too influenced by individual data points. And that's overfitting. You're fitting those data points too much. The best example of overfitting is when you study for a test in a class, but you just memorize all the practice problems. So if you don't actually understand the material in a course on linear algebra, and you say, I just memorized all the practice problems they gave me, then if they give you the exam and they are testing you on linear algebra, then memorizing the practice problems is not enough to do well. You have overfit to the practice problems on the test. On the other hand, if you have learned the lessons of linear algebra by doing the practice problems, then you will do well on the midterm. That is like correctly fitting. So overfitting is like overly memorizing the examples you were given. This is a perfect example of overfitting, and that is the high variance, low bias situation. On the other hand, this is underfitting. So in underfitting, you're being sort of too rigid. You are not using enough flexibility to move your function. And in fact, this function, it has very low variance because it's almost always a constant that is very close to the number 6. So it's sort of always outputting the number 6. Okay, very low variance, but is not flexing enough to curve to match what we want. So that is underfitting when you don't bend enough, and overfitting is when you bend too much. We're going to handle these things mathematically in a second, but this is the right kind of picture that you need to imagine in your brain. Any questions or comments? Underfitting versus overfitting in this example? Yeah?
How do you get the blue curve?
How do I get the blue curve? The blue curve, remember, is the true thing that we're trying to get. In real life, of course, you don't have the blue curve, right? So right now, the blue curve was used to generate the data. And then we're doing this to learn about how this stuff works. And so we can easily see when is the purple curve far from the blue curve or not. And we know that far from the blue curve is lots of error, close to the blue curve is small error. In real life, of course, you don't have access to the blue curve, and you have to first learn all the lessons and then sort of like apply what we know to figure it out. Yeah, that's a great point. All right, any other questions? Yeah?
Is the blue curve the estimate? If the points are with how far the curve will reach, is the blue curve the estimate?
No, the blue curve is not the estimate. The blue curve is the true function f. The blue curve is the Platonic ideal that we are looking for. So the blue curve is the graph of the function f, which is this thing, the true mean of the y values. And the purple curve is the function f hat, which is our estimate based on the data that we saw, right? And we would like the purple curve to be as close to the blue curve as possible, but we don't have perfect knowledge. The only thing we're allowed to use is our samples, the dots, right? So we're trying to use the dots to construct the purple curve so that it is as close as possible to the blue curve. That's the game. And in real life, you don't have access to the blue curve at all. So in real life, when you get a data set, it looks like that. And you're like, am I close to the blue curve or not? You can't tell. You have to do something else to check. We're going to talk about this, how you would check later on. But I think it is important to theoretically know what we're doing. We're trying to get as close as possible to this curve, even though we can't see it in practice. Yeah, absolutely fantastic question. So this is like, the way we're learning about this is we're cheating and looking at the blue curve, so that when we go into real life and we don't have access to the blue curve, we can take the lessons we learn and sort of get better. Okay. Any other questions or comments? Okay, let me finish doing a little bit more math on this thing. So we have the two situations that I said. We have so I've decomposed this term by adding and subtracting something and using Pythagoras. This middle term, f hat minus f, is two parts. It's how far is f from its mean, and how far is its mean from the true f. And those get added together. I wrote an equal sign here, but that is incorrect. These get added together. Okay. So this is a big plus. And there's one term I'm forgetting. Does anyone know the term I haven't written down yet? I heard someone say it. Yeah, the irreducible error. So remember, there's how far f hat is from f plus the irreducible error, right? You can't forget the irreducible error. So plus the expected value of x times the variance of y given x. That's the irreducible error that you will never beat. So that is this term over here. So there's really three kinds of error in general. There's the irreducible error. Even if f hat equals f, if you get the perfect exact thing, you do as well as you can never escape the irreducible error. But then you also have a bias, which is how far are you on average, and then you also have a variance, which is how far are you jumping around based on the data set. And you want to minimize the sum of all of these three things. Of course, this one you can never do anything about, so we're really minimizing the sum of these two things. Let's talk about these two things and how you would minimize their sum. Okay, and so the key thing is in our problem, let's understand everyone, or most people saw that this was an underestimate. So let me put this guy back. So as you make the window size bigger, it's an underestimate, and you should be able to sort of intuitively see why it's an underestimate. The reason, I'm going to write it like this. So why is it an underestimate? And this will also help us understand how things scale. So why is f hat an underestimate at x equals 45 degrees, and how big? This is the main thing I want to get to, is how big is it, roughly. So how big is it roughly will help us balance these two things. If we can answer the question, how big is this term and how big is that term, then we can minimize their sum. Okay, so why is it an underestimate and how big is it roughly? The key thing, what is the average of the f hat in this situation? I'm gonna tell you a formula, and then I'm gonna justify why the formula is true. And so really what f hat is doing is there's the true f over here, which is the true average. F of x is the true average. And we are averaging a little chunk of that. So the expected value over all the training points of x1, so x1 to xn, y1 to yn, we are grabbing a little slice of the f, and we are averaging it that way. So the little slice of the f we're grabbing is from, there's x, and then there's x plus delta, and there's x minus delta, and we have this whole little region, and we're averaging it all together. So we're doing the average of this little region. Let me shade it in with a highlighter. That'll be cool, yeah. So this little shaded region over here. And we're averaging the value of the true f over here. Averaging in mathematics you can express as an integral. So this is an integral. It's the integral, let's do it with a pen. It's the integral from x minus delta to x plus delta divided by the length of the interval, which is 2 delta, of the function f of x dx. So our procedure of estimating f hat, based on the way it works, is it grabs all the sample points between minus delta and plus delta, and so we're averaging the true average over here. And when you average this thing, what is going to happen? I claim that this is less than, at 45 degrees, this is less, the average is less than the value. And you can see that on the graph. The average of the point is somewhere over here, or the true value is up here. That's f of 45. And the average value is somewhere less. Let me zoom in. Let me make a zoomed in version so you can see it even better. So here's x minus delta to x plus delta. To make it look really extreme, I'm going to exaggerate the features. So it looks like this. There's something like that. And we're at the very tippy top, the maximum. This is f of 45. And we're averaging the value of this function over this thing. And the average is going to be somewhere less. So the average is over here. So the average value is here. Maybe I'll write this. This is the average, the integral from 45 minus delta to 45 plus delta, 1 over 2 delta times f of x dx. So this is some point that has the same, this is some rectangle that has the same area as the function f, but is going to be lower because this is the top. So these sort of parts where it's sloping down, that is pulling down the average. So the average is always less than the maximum value. And if you wanted, you could estimate this by estimating the whole function. So you could estimate this whole thing as a quadratic equation, and you would get an estimate that looks something like this. So this is approximately f of 45 minus delta, and it's going to depend on the second derivative, f double prime of 45. So if you took a good calculus class, you'll know how to do Taylor series expansions. This is a Taylor series expansion where we approximate the function f by a quadratic equation, and we say the average value is approximately that top value, but then minus something that depends on how concave down it is. So if it's very concave down, it's a really bad underestimate. If it's kind of flat, then it doesn't matter so much. So I'm going to skip the details on this because they're not super important for us. So this I'm going to skip details here. But this is by Taylor series expansions. Skip details. What is the punchline of all this? The thing that I want to get to is, therefore, in this problem, the bias, which is how far is the average from the true value, it is approximately the delta times the second derivative, f double prime of x. And what this means is if you make delta twice as big, you sort of get twice as much bias. This is the important thing for us. Delta twice as big has twice as much bias. So you can see that sort of in the picture over here if I make the window size. So if the window size is sort of really small, on average it's correct. But then if I make the window size much bigger, then it is going down and it's proportional. So if I do this, it'll be a certain amount. So I guess we have to wait for a few to see on average how big is it. Let's see. This is like, I think this is about one unit underneath on average. And then if I double the window size, so here the window size was 15. If I double the window size to that much, it should be like 2 units underneath. Is that approximately true? So 1 unit, 2 units. It'll be here on average, if what I'm saying is true. And it looks like it is approximately correct. So the point is, the bias is proportional to the width delta in this particular problem. Why is that important? Well, so the bias, it is like delta, and therefore the bias squared is like delta squared. The bias squared is like delta squared, f double prime of x squared. Okay, so that's the bias at the point x. It's going to go like delta squared. This is great because if we know how big the bias is roughly, then we can sort of minimize the bias and the variance. The variance we've already done. Let me remind you what the variance is in terms of delta. The variance that is in this problem is just the sample size. So the variance, which is the expected value of f minus its mean, f hat minus its mean, squared. I'll write it like this. This is, we said before, this is 1 over n, where n is the number of points. N equals the number of points in sample. And that is, okay. Again, the number of points is not exactly always fixed. Sometimes you have, by chance, you have more or less. But in the situation where we did it before, it was exactly 1 over n. In this case, it's morally 1 over n. I guess it will be like the expected value of this. Okay, and this is approximately 1 over delta. This is approximately 1 over delta. Or actually, in this case, it's 30 over delta. Why is it 30 over delta? Well, there are 30 points, right? There's 30 points. So if you look at a window size of size delta, then you get a fraction of 1 over delta of the whole thing. So it's like 30 over delta. I guess more accurately, it's 30 over, and then you have to do delta. What fraction is delta of the full 90 degrees? So maybe it's 30 over delta over 90. Delta over 90. Again, I don't want to get bogged down by exactly what it is, because I just want, the thing that I want is the following. The variance is approximately like 1 over delta times some constant a, and the bias is approximately delta squared times some other constant b. And so these two terms will play against each other. Our job is to minimize, this is the bias squared, minimize 1 over the sum of these things. So minimize 1 over delta times a plus delta squared times b, and we're going to find the delta that minimizes that. And what does this look like? The reason I wanted to get it like this is now we can draw a nice graph of what this kind of thing looks like. So let's draw that graph and take a look. So it's a function. Let's make a new graphing calculator. And we have some constant a, let's make that 1. We have some constant b, let's make that 1. And we're doing the function a times 1 over x plus b times x squared. And we get this nice curve that looks like this, where, oh, I put in cubed. Let's fix that. Okay, so we have this curve, and it should look like this, where it's kind of shooting off to infinity. If delta gets really close to 0, that's going to blow up. If delta gets really big the other way, it's also going to blow up the other way. And there's a sweet spot in the middle. That is exactly what we want to do. We want to find the minimum value. Okay, and depending on what A and B are, this might look a little different. So it might look more like this. You know, it could be very flat, like that. If B is small, a big number or a small number, it can look like different things. I will say it does not look like this, because in this situation, B is negative. A and B are both positive numbers, so maybe I should start my sliders off at 0 for both. But this is roughly what it's going to look like when we're trying to minimize the value of delta. And finding the value of delta that minimizes it is meaning we have better error. We are predicting things as well as we can, finding the Goldilocks zone for that window size. Okay, let's do that in practice. Here is how I'm going to do it. To start with, I'm gonna in a minute. I'm gonna get to a real graph like this. But before we do that, let's play around with. So we've done all this math, and let's see if it actually works in our data set. So I'm gonna pause this so we stop making new data. And what I'm gonna do is I'm gonna have a little screen down here that tells us the error size. Where's the error size? The error. That's not what I want. There's a little thing here, error label, here it is. And the error visualization. Okay, this is lovely. Okay, so what is this doing? So not only do I have the purple curve and the blue curve, now I've drawn where is an underestimate, where is an overestimate, and I have calculated the root mean squared error, which it claims is 2.18. And this is doing exactly what I said. This is finding the difference between the blue curve and the purple curve and squaring it everywhere and then adding it all together. You might notice this word root, which I have not said yet in the course. So far we've talked about the mean squared error. Everything's been the mean squared error. And then all of a sudden I throw this root mean squared error. So what is the root mean squared error, and why did I do it? Has anyone seen this word root before? This is the acronym RMSE, which you might have seen.
Keep the number positive?
Well, the number's already positive because it's an average of squared things. So I could have said the mean squared error is like 4 point something, or I could have said the root mean squared error is 2 point something. The root, it just means square root. I took the value that was on the board. All this theory we've been doing so far is all about sum of squares of things, right? This was a square thing, you add it to the other square thing, you add it to the other square thing, and I'm saying do the square root of the whole business. Why on earth would you do the square root of the whole business? Why should you do the root? Yeah.
It works out to the positive mean error.
It works out to the positive mean error. Yeah, I think you're getting at the right idea. Maybe you want to say a few more words. I think that is true, but do you want to explain a little bit more?
Well, if you have the error, you can be wrong in either direction on average.
Yes.
So that'll work out to 0, assuming everything's
right.
equal. And you don't want that, because if you're getting things wrong consistently, that's
right.
obviously bad. So you square it, now everything's positive, now you have a number you can use, but that doesn't tell you how much you're actually off by on average.
Right. Yes, okay, this is very nice. So the point is, when we take the square, taking the square made all our math really easy. It made the Pythagoras formula work, and it made negative and positive errors both count as bad, and everything worked out. But the problem is, if we're doing just the square error, it sort of has lost its meaning, right? So if the square error is 4, then what does that mean? Well, it's hard to say. But if the root mean squared error says, on average, in some sense, you're off by 2, right? So the units here are saying, if it's 2.18, then I should expect if I take a unit 2 meters wide, that typically we're about 2 meters off. So we're a little over 2 meters here. Here we're a little under 2 meters. But we're on average, we're off by 2 meters in some sense. The amount of error we have is exactly the same as if we were always off by exactly 2 meters. And that's why we take the square root to sort of make it interpretable on our graph, so that it gels with the units we're using here in meters, and it is interpretable as saying we're off by 2 meters kind of on average, in some kind of average sense. If you didn't have the root, then you would have to do the square root of like 4 in your head to figure out what you're off by. So it kind of takes it from abstract to more interpretable. So that's why all the theory is done with the mean squared error, and then when you go to plot it or have somebody understand, you do the root mean squared error so they can understand. I will also say, you might recognize the root mean squared error would be the square root of these 3 things added together. That is exactly like a Pythagoras formula, right? So you do the square root of a squared plus b squared. That's the thing. You have all the contributions from these 3 sources of error. You square them up. These are squared errors, square error, square error, square error. And then you do the square root of their sum. That is the total error. Okay, so the root mean squared error. And what are we doing? We want to make it as small as possible. So if I make this window size too small, then the error is big. It's like 3.7. We're off by 4 meters almost on average. And if the window size is too big, then we're also kind of have bad error. So here's an error of size 3. We're off by 3 on average. Why are we off by 3 on average? Well, here we're consistently underestimating. Here we're consistently, here we're overestimating, and there we're underestimating. But there is a sweet spot in between, and we can sort of just drag this around to find it. So 2.9, 2.8, 2.7, 2.6, 2.4, 2.1, 1.9, 1.6, 1.4, 1.3, 1.2, 1.1, 1.0. Oh, we have less than 1 meter of error. This is amazing. 0.7. Okay, but now you see it's starting to go up again. So I went too far. I gotta back it off a bit. Okay, 0.7, 0.8, 0.75. Is that the 0.73? I saw 0.73. I think that's about right. So this, according to our calculation down here, is the actual minimum we can get. And I did it just by playing with the values and seeing where was it as small. I also did a more detailed version of the calculation that I did, and I came up with a theoretical version. So here's the theoretical, just based on pen and paper math, where should the actual minimum be? And it says it's at, the optimal window size is 11.58. That's like how far we are. And I think this is just a little bit bigger. So according to me, let me see. I think I have a thing for the window. Where's the window slider? Here it is. Okay, here. So right now the window is at 17.6, and this thing says the optimum should be at 11.58. If I change it to 11.58, then it'll probably go a little higher than 0.73. 0.73, and I want to make it 11. Ooh, it's quite a bit higher. 11.58. So then we got quite a bit more. But you know what? We can see how it does on average. We can check how it does on average by generating more data. So if we flop the seed around, then we can see which window is better or worse. And okay, so here it's 1.3. Oh, and it's a bit smaller this way. So the theory is kind of saying that the window should be 11.5, when in practice, what we're doing is it turns out it looks like 15 is closer to what we need. But a window size of around 15 is the optimal here. We're going to go into more detail on this in a second. So is the theory perfect? No, but it gives you the right kind of sense of how big things should be. Okay, we're gonna do this in more detail in a Python script in a second. But any questions or comments about this thing? Okay, I do think this is like the most critical lesson in all of this data science class for the first half of the course, is this underfitting versus overfitting idea. That when you are tuning things, you are trying to balance 2 things, right? The bias and the variance, and there is a sweet spot in between. I think a lot of people miss that, and they say, just like make the window 100% small. Look, if you make the window as small as you can, then you are getting lots of points that are right on the curve. And they make mistakes like that. Whereas in reality, there is a sweet spot, and understanding this, like why this happens, is like the key. This lesson will generalize to all the other things we do in this course, like linear regression and all sorts of more complicated things. Finding the sweet spot is always there. Okay, I'm going to move to the Python script now. Any questions or comments before I do that? Why am I going to move to the Python script? Because we could slide this around all day, or we could have the computer draw a graph. And we'll see that the graph looks a lot like this graph that we have. So I'm going to move to the Python script now, if I can find it. Let's see, where's my Python script? Okay, it is on the course GitHub. Let's go find it. I have lost track of it. And I want to go to weighted average estimates. And I'm going to open it in Colab. Let's see if this works. Okay, amazing. So this is the way we're going to do Python in this course. So when we start programming things, it's all going to be in Python. And I'm going to use mostly this Google Colab, which lets you also write down math equations and lets you run everything sort of in a nice, easy to run way. I'm going to run it anyway. And look, this is all the math we've been doing so far. And here is some of the things that were in the Desmos graph that are now in Python. And one of them is the secret mean function. This is the blue function that we had before. And this is the secret variance function. But altogether, you get the same plot as in Desmos. There's the secret mean function in blue, and there's the data that is above and below. OK, and then we can do our average estimator. Here is how you would implement it in Python. It is f hat is a certain sum divided by the number. You can also generalize it to any weight. And it will look like this. So here are some different values. This is exactly like what we did in Desmos, but now in Python. So this is a pretty wide, this is delta equals 30, a pretty wide window. And you can see it looks like that. And this is delta equals 20, more narrow window. This is delta equals 10. And this is delta equals 5. And this is delta equals 2. Delta equals 2 is jumping up and down like crazy all over. OK. The real reason we wanted to do Python is so we could do this graph. I'm going to come back to this one in a second. But we wanted this graph over here, which is, this is, on the x-axis, I have delta. So how big is the window? Let's see if I can get it to go right. So how big is the window? Window size 30 over here, window size 0 over here. And on the y-axis, I have the root mean squared error. I have also plotted two different dashed lines. The bottom dashed line is, again, something you would never know in real life. This is the minimum possible thing. This is the irreducible error. It will never, ever be possible to go below the irreducible error, because that's always there. Over here, I have the estimate of a constant. So if you were to just forget about the x's and say, forget about the x's, I'm just going to estimate the average of all the y's, then you would get this much error. And this green curve is exactly the kind of curve that I was showing in Desmos. This is the combination of the bias squared plus the variance. This is your total error that you can get. And you want to find the minimum. The minimum happens here at right around somewhere between 10 and 15 is the minimum over here. So this is very nice. It matches all the kind of things we've been saying. You want to balance these two things. One of them blows up at 0. One of them blows up at infinity. You want to balance them and find the right balancing point. OK, great. Let me also quickly say, what is this red curve? The red curve looks just like the green curve, but it's a lot smoother. The green curve has these like bumpy bits. And actually, if you look at our plots, right, our plots that we've been doing, they're kind of bumpy and jagged and kind of ugly to deal with. Like they kind of have these like vertical segments and so on. And the reason they have these things is because when we do this averaging, there's this cutoff phenomenon where, let me go back to the local averaging. Like you see when I'm changing, I have a certain point. Let me make it really small, and then it'll be more obvious. So if you look at this thing, it's going for a while, and it suddenly jumps up here. Why does it suddenly jump up here? Let me slide the thing over, and you'll see why. So it jumps up here when all of a sudden it's equally far away from these 2 points. So on one side, this was the closest point. On the other side, this was the closest point. And when we're in the middle, it's exactly switching over from this one being the closest to that one being the closest. So there's these like ties that get broken at these jagged points. That's kind of ugly. We would like to not do that. And that's why in here, I have also done something called the Gaussian weight, or the Gaussian kernel. So you have this weight function, which is how far away you are, divided by sigma squared. And this is sort of balancing things in a smooth way. So instead of saying you're in or you're out, all of the points count, but they count with a weight. So instead of averaging all the points that are close, so instead of for the red curve, instead of saying only the points that are nearby count, all the points count. It's just the ones that are closer count more, and the ones that are further count less. And the way we do that is this Gaussian weight. So this is called a kernel function. We're not going to use these a whole bunch, so if you want to sort of learn the details, you can. But you should just think of it as a smoothed out version of what we were doing before. So it's nice and smooth, and that's why these curves are less jagged than what they were before. And you'll see even if I make delta quite small, so here sigma is the characteristic width, is pretty small, it's 5, and it's jumping up and down, but it's not like vertical, it's jumping up and down in a sort of reasonable way. And here it is, it's still smooth. Here it's starting to be more vertical because I made it only 1. So it's points that are within distance 1 count a lot, points that are far away count much less. So it's more jagged, and you get a nice smooth curve for the error. Okay, and so this is the game. You set up your procedure, and then you're going to optimize these parameters to find the minimum possible weight. Having the minimum possible is a lot less than if you just picked randomly. Like if you pick 20, you'd have a lot more error than here. Of course, it's error in a relative sense, right? We're going from an error of about 4.1 for this spot versus like 4.4 for that spot. And is 4.1 a lot less than 4.4? Well, yeah, because the minimum possible is 4. But in sometimes, in an absolute sense, it's not much less error. So that is the game. I'm going to write that up in 1 second. Actually, let me write that up and then I'll take questions. So this is the sort of workflow for data science. This is our like general workflow. So step 1 is collect data. Often this is done for you. So I'll say get data, and data means x's and y's. And then step 2 is decide on a procedure. And the example we just did is the nearby averaging, or kernel averaging. Nearby / kernel averaging. That was what we used for the cannonball problem. And this had one so-called hyperparameter. This is a hyperparameter, which was delta or sigma for nearby, near neighbor. And this was for the Gauss kernel. But they both kind of mean the same thing. So we had one parameter, delta or sigma. And in step 3, we optimize step 3. Find the value of the parameters, in this case delta or sigma, to minimize the error. Minimize the error. And this is where you be careful. Do not overfit. Do not overfit. But also do not underfit. So that's why you have to balance it. And in practice, the way you do it is you make some sort of graph like this, and you find the minimum. So you try a bunch of different values, and you find the minimum value. Okay. Questions or comments about the general workflow or anything else that we've done so far? Okay. All of this is very nice. This is like how you should think about things. But there is one actually very important detail that I kind of glossed over. And the problem is that in reality, you can never actually get this curve. So it would be so nice if you could just plot this curve, find the minimum, and then be done. But I cheated, and I did something that's not allowed. And the question is, what did I do that is not allowed? So that is finding the sweet spot. In real life, we cannot actually compute the MSE because we don't have access to the blank. So I cheated, and I did something that I wasn't supposed to do. So what did I do that was wrong when I made the thing? Okay, I will let you guys think for a minute. Feel free to talk to your neighbors and figure out what did I do that was cheating. Okay, 30 seconds left to tell me what you think. We don't have access to the blank. Okay. Let's see what you guys said. What did I do that was not right in this whole little presentation? We don't have access to the RMSE. So I think it's true we don't have access to the RMSE. Why don't we have access to the RMSE? So this RMSE that we wanted is that I was plotting over here. If we had access to this RMSE, then I would be so happy. I will also say RMSE is sort of like the label I have over here. But RMSE is telling you like what we're measuring, but not like what it is. What it is actually this thing. It's the true error in the nearby neighbor averaging, is the green curve. And the true error in the Gauss is the red curve. So the RMSE is like kind of like the units are like what we're doing, but this is like the thing. We're measuring the true error, the RMSE, where E stands for the true error, and it's this curve. And I don't actually have this. But why not? How come I can't do it? Why can't I just calculate the RMSE? That's what I'm asking you. So again, first answer, perfectly true, but what is it? And someone wrote the population distribution. So the population distribution would mean the true distribution of all the x's and all the y's, like perfectly specifying what is the probability of having any individual xy pair. And I don't have access to that, but I don't think I actually need this. This never entered into my calculation. I never had a calculation where I needed to know the probability of x and y. So I don't have this, but I also don't need this. So I need something that is like related to this, but not as detailed. And so someone wrote the true value function. The true value function. Value function has a specific meaning in reinforcement learning, say. So the true function is the thing I'm missing. The real function, the true y, that is what I'm missing. It's the true function, which I called f. Did anybody write f? True f of x. There we go. I think this is the nicest way to say it. The real function f. That was the thing we were trying to estimate. The true value, the real one. These are all the right kinds of things. We do have the samples. What we don't have is the true value f. And so that was on the Desmos. That was the blue curve over here. And that was in my little thing. That is the blue curve over here. And then I was calculating the error by how far is the estimated curve, the red from the blue. But in real life, you don't have the blue. If you had the blue, then you wouldn't do this whole game. So even though my procedure to calculate the red curve only depended on the data, my procedure to calculate the error of doing the square difference between them depended on the blue curve, and that's not allowed. You don't have the blue curve in real life. So unfortunately, the workflow that I wrote over here is not going to work, but we can modify it by just replacing the error with something else. So instead of finding the error, we're going to estimate the error. So I'm going to replace find with estimate, and so what we're going to do is, instead of doing the true error, we're going to have some kind of estimate for the error that we can get from the data. And this is the topic of the videos you've been watching. So there's actually going to be a step 3a, which is going to be to split the data you have into a test set and a training set. So split into test set and train set, and train set. So all the data we have, we cut it artificially into two pieces, the test set and the train set. When we do our procedure, we do it only on the training set, and then we use the testing set in step 3 to minimize what kind of error? The test error. And we cross our fingers and hope that the test error is a good approximation of what would happen if we did the real error. So let me show you what that looks like in Python. And once again, what I had on the board before is what we would like to do. And then this is what we do in reality, because you cannot actually do what I wanted to do. You have to do something slightly different. Okay, and so what we're doing is we're doing a division of the data set. We first divide it into two parts, a train set and a test set. So here I have taken all the data and I have replaced some of them, I think of them as training dots, and some of them I think of as testing x's. And the rule is when I do my averaging, I only do it on the dots, and then I'm going to use the test data to measure how well are we doing. Okay, so for example, here is the estimate with sort of a window size of 30 and only using the black dots. And the nice thing is when I only use the black dots, I can use the pink x's to measure how far away we are. So a good example actually happens on the other end of the spectrum. Here is a great example. if somebody said, this red curve that I did, is that a good estimate or a bad estimate? Well, if you're only using the black dots, you would say that's a great estimate. Look, we got it exactly right. Over here, we got it exactly right. Over here, we were off by a little bit. But over here, look at how close we were. That's amazing. You say that red curve is a great estimate. But you would be wrong, because this is actually a very bad estimate. And you can see that by looking at the pink x's. So the red curve, which was using the black dots to train, you should measure it with the pink x's, which are the test set. And then you will see that it is quite bad. So this is the idea. We split our set into two parts, and we estimate anything we want to know about error, we estimate it with the test set. Let me write down some mathematics to put this down. So the true error, or the true mean squared error, that's right, MS error, mean squared error, that is the expected value over the actual things of how we do f of x minus y all squared. That is the thing we've been working with up until now. All of the errors have been the true errors. But the test error is something else. The test error. This is an approximation. And what we do is we average over our test set. So we go over the number of test points, and we do the sum from I equals 1 to the number of test points, and we do f of xi minus yi squared. So in other words, we're approximating a theoretical average, the true error that we want, with our test set, and we're just doing the average of our test points, and we cross our fingers and hope that these are close together. So we say should be close together, should be similar if we use enough test points. Okay, that's the idea. And we can never calculate this one because we don't know the distribution, we don't know the true value of f. I have a mistake on the board, which is this should be the hat, right? The hat. Okay, so let's say of f hat. Okay. And again, this one decomposes in terms of the true f, and you can think of these as being written in terms of the true f, but in real life, you don't have access to the true f. You can just think about it. You'll never actually know it, and you'll never actually be able to calculate quantities like that, but you can calculate these things and make your decisions that way. Okay, so if you use that formula, and you use the little thing over here, then the blue curve is what I had before, was the true error, which is unknown in reality. That was the curve we were minimizing before. And the red curve is what you get on just the test set. And you can see that they don't actually line up. They're actually quite a bit different. But the choice we're making is what is the best possible value of sigma. Those are pretty close. Where the minimum happens on the blue curve and where the minimum happens on the red curve are pretty close together. And so our procedure works pretty well. So even though we can't find the actual true minimum, we can get pretty close by doing this estimation procedure with the test set. And that is the workflow I wrote over here, right? So when you're making your choices, you don't make your choices based on the true error because you don't know the true error. You make your choices based on the test error, and hopefully the test error is representative enough of the true error that your answer is pretty good at the end. Okay. Questions or comments about this procedure? Yeah?
So over on the graph,
Yes.
The reason it dips below is because of the irreducible error is packed into the test set?
No, the reason it dips below the irreducible error is because the irreducible error is a statement about what happens on average, in the true average. So if you get unlucky or lucky, depending on how you do it, an individual data point could be below the irreducible error.
Yeah.
It is a bit like when we rolled the dice, and I said, on average, you owe me five quarters of a dollar. So the irreducible error is 5 quarters. You will owe me 5 quarters of a dollar on average. But on an individual roll, or even on 10 rolls in a row, you might owe me much less than $1. And that's what's happening here. So the test set is a randomly chosen set of points. On average, its error should never go below the irreducible error. But for a given realization, it could definitely be below. Yeah. Yeah, and I think the way you should think of is there's this thing, the truth that we want to get to, and we have some kind of noisy estimate that is maybe like up, down, move left and right, that kind of jumps around, and on average, it's where we want it to be. And we just need to be close enough that when we make our choices, we're not way off. Yeah, fantastic question. Any other questions or comments? Okay, I have 2 mathematized questions about this. The first one is a very common, once we start doing the project, which is coming soon, And so the project will be posted soon. You'll have to do this kind of procedure on a real data set. And this is a very common error that students make. So they're working on the cannonball problem, and they say, I made a plot of the root mean squared error, and it doesn't do what you said. You said that the error is supposed to go sort of have this sweet spot and then it goes up, like it's a U shape. I made a plot of the error, and it just keeps going down and down and down. The error, and it goes down and down and down, right? It looks to me like I should make sigma or delta as small as I want. And the error is not getting bigger, like you said. What did I write over here? It seems like the error is getting smaller and smaller. I do not see the U-shaped trade-off curve that you talked about in class. This student has made a very common mistake. What is it that they are graphing? What is this actually a graph of? They have plotted the wrong thing. Okay, I will give you a minute to think. What could be going on? And again, feel free to say, I don't know, or 5, 4, 3, 2, 1, if you have no idea. Okay, 30 seconds left to tell me what you think is going on. Of course, you might have no idea, which is totally fine. All right, 5 seconds left to get your answer in, even if it's I don't know. And let's see what you said. Okay, so fundamentally what's going on here is there are, the word error has become very overloaded. There are many different types of error. If you say the error is so much, which error are you talking about, man? So there's like 10 errors floating around. There's the irreducible error, there's the error due to this part, the error due to this part, there's the real error, the true error, there's the test error. What did this person actually plot? I don't know. Let's see what they said. Reveal. Okay, so error, yeah, this is, if you said error, you have fallen into the trap that the student fell into, which is thinking that there is one error. If you say the word error and you don't know which error you're talking about, you're going to have a bad time. And part of the problem is when people talk about it, like if you're having a conversation with someone, in the first sentence of your conversation, you will establish what you're talking about, and then you will use the word error, and it's fine. But the problem is, like, if you don't know what the error is, then is an issue. This person is overfitting. They are overfitting. But the thing that 3 people got, and that is exactly the correct answer, is they are plotting the training error, and they are mixing up the training error and the test error. What is the training error? I have not even said what it is yet. Let's write that one on the board. And just so you know, not to mix it up. So far, there is the true error, which is what we actually want to minimize. There is the test error, which we are hoping is a good proxy for the true error. But there's also something called the training error. The training error. The training error of f hat. And it's the same exact formula as this, except instead of being over the test points, it is over the training points. So I'm going to call this the test, the x test and the y test. Those are the points we held out for the test. And so this is the number of training points and then you do the same kind of average over all these points. So exact same formula, but different interpretation. Minus the yi train squared. Okay. And you might think, hey, the test error we said is a good proxy for the true error. Shouldn't the training error also be a good proxy of the true error? And the answer is no. This is, I think, the most important thing you should know about the training error. Or as I wrote it, the training error. Warning. The training error, this training error is not, in big capital boxed letters with lots of exclamation points, it is not a good proxy for the true error. So you should not, even though we would like the true error, we can't ever get to the true error, so we use the test error instead. And the formula for the test error and the formula for the training error look very similar. But the training error, nevertheless, is not a good proxy, and the test error should be a good proxy. The training error is not. Does someone see why the training error would not be a good proxy, even though the test error is, and their formulas are very similar? What's the deal? Why is the training so different than the test? They're both points, right? Why does it matter which one is which? Why should it matter so much? Why should it be such a big difference? It is. So this is essentially the idea. This is one way to describe overfitting, is that your training error is very, very small, but the real error, or the true error or the test error are very high. That is one way to describe overfitting. And so that is a situation, you have pointed out a situation where the training error is not good. So let me write that down. I think that is worth doing. So example, overfitting is an example where train error is very small, so very close to 0, but true error slash test error is large. So overfitting is one particular situation where the training error is very small and the other ones are large, which is an example of where this principle is happening. But it still doesn't get to the core question of why is that true? Like, look, the formulas look exactly the same. If I said this formula, what's the difference? You'd say there is no difference. It's just a different bunch of points. So why is it that one of them is okay and the other one is not? Yeah.
Because the hyperparameter is set so that
Yeah.
like the errors should be similar. The training error.
You're on the right track. So it's not the hyperparameters, but it is the thing that you're right in that it is a secret thing that is not on the board, like the hyperparameters, but it's actually the function f hat. So the function f hat, I just wrote it down over here. But if you remember, how did we define f hat? F hat was already defined using the training things. So when we write f hat, the thing I didn't write is that f hat actually depends on the training set. So f hat, so you can say because f hat of x actually means f hat of x, and it depends on all the training examples. X and train, y1 to y and train, right? So the function f hat was a function that depended on the training data points. So we have already sort of used the training data points to calculate the function f hat, right? Our estimate depends on the points we're training on. And so we're sort of double dipping. When you use the training points to both calculate f hat and compute the error of f hat, it's not right. But if you use f hat, calculate it on the training points, and then you calculate the error using the test points, because those two data sets should be independent, this should be a fair assessment. And in particular, like you can see in our nearby neighbor averaging problem, the problem is super obvious in that as soon as the window size is really small, like as soon as the window size is small enough, the error, the training error is 0, right? The purple curve perfectly goes through every single training point, 0 training error. But the real error is quite large, because the how far away are we from on average is quite large. Okay, I actually did not make it small enough. Like there's one point over here where I have some non-zero error. So I just have to make the window even smaller. Can I make the window even smaller? Okay, I'm gonna cheat and re-roll. There, okay, now I have zero training error. And this window, this averaging thing, will always have 0 error if you make the window size small enough, but it'll have 0 training error, and that is not what we care about. So this is a very common mistake. Don't fall into this trap. Always make sure you know what kind of error you're plotting. If you have a plot like this, and it doesn't have the word training or test or true on it somewhere, you're gonna get mixed up. So it's good to always know what error are you talking about. Okay, that's where we're gonna leave it for today. Next week, we're gonna start talking about linear regression in a lot of detail. Everything we've said so far will still apply to linear regression, and it will have some more details to figure out. Okay, let's pause there.